think basically if I were to pitch Toffee, first time to someone who's never heard of us, I would say that we are primarily a optimization and simulation tool for thermofluids, right? So it's quite specialized, it's quite niche. We're not here to solve all of your engineering problems, but if you have a thermal management or a thermofluids problem, then I think we are an essential part of the design process for that. It's a slightly different tool from what people are used to working with, and that's absolutely correct. It's new. It doesn't quite fit into any sort of different. It doesn't really fit into a specific bucket, but it is an optimization and design tool for thermofluids.
Got it. When we talk about some application, Thomas, what I would think about first when I hear this is heat sinks. Is there anything else that people can imagine when they think about Toffee?
Yeah, absolutely. So basically, it's let your imagination run wild. Heat sinks obviously is very important part of our business. So both actively and passively cooled heat sinks. But really things like cooling plates, both on small scale, so for like small inverter or power electronics, or large scale, so things for like battery packs in electric vehicles, heat exchangers, two fluid heat exchangers, air, oil, fuel oil, air, fuel heat exchangers for energy and aerospace primarily. Manifolding problems is another big thing we do from in automotive and aerospace, where it's fuel delivery or exhaust manifolds, or even we work also now more and more in things like manufacturing. So injection runners for like high pressure die casting is a manifolding problem. It's a fluids problem. That's something we work on as well. So it's any sort of internal fluid dynamics or thermofluids problem. We've managed to find some success in almost everything we've worked in.
Yeah. When we think about the heatsink, I think it's probably the easiest example for people who are listening to this podcast. How does the interplay work between, let's say, the generative part, the generative design part, and the topology optimization part, as well as the CFD bit of it?
Okay, so maybe we start answering that question with some definitions then. Yeah. All right. So I think we start at the most basic, which is CFD is quite ubiquitous now as a tool in terms of reducing cost of development for engineering problems. It's much cheaper to run computational simulations now for fluids than to buy some time in a wind tunnel. And CFD is really the basis of what we do, right? So underlying almost everything we do at ToffeeX, there's a CFD simulation. On top of that CFD simulation, we have a topology optimization tool. So what is topology optimization? So topology optimization, it's I guess you can describe it as an algorithm, but like it's a mathematical process, optimization process, which allows users to create optimal designs for something that obey certain rules of physics. So if you imagine in our context, we want to create an optimal design for a heatsink, right? And there's certain requirements for what is optimality in a heatsink. So the classic examples we use in all our communications is you want to minimize the pressure loss of the fan blowing the air across the heatsink, and you also want to minimize the temperature of the thing you're cooling. So you can write this mathematically. You can write, minimize my pressure plus temperature. But that doesn't tell you anything about what you are allowed to do with the pressure and temperature, right? It's very easy if you want to minimize it. You say pressure equals minus infinity and temperature equals minus infinity. But, this is obviously nonsense. So you need to give some more information to the optimizer to say, minimize my pressure and temperature, but also you need to follow these rules. And so in our case, and in topology optimization, the rules are the physics equations and the fields given as solutions, but these physics equations, which we calculate with CFD, obviously. But if in more conventional topology optimization for things like structural problems, they solve linear elasticity with finite element solvers. And so, that's like the really high level sort of basic description of topology optimization. It's an algorithm. It allows you to optimize with certain constraints which represent physics. At the top level then, you mentioned generative design. So generative design is more of a, maybe it's more accurate to describe it as a philosophy or something like this, right? There's no one generative design. And if you ask different people in different industries, it will mean slightly different things. But I think probably the most uncontroversial way of describing generative design is that it's a design process where there is a computational algorithm generating designs based on inputs from a user. So there's like this process where a user defines inputs and selects an algorithm. And then the algorithm takes these inputs and runs and generates loads and loads and loads of designs, right? And then at the end, you have loads of designs, and then it's back to the engineer or the architect or, you know, the industrial designer, whoever's using the generative design tool, to use their own, you know, expertise and, you know, experience to dig into all of this messy data, some of which may be nonsense and some of which you hope is really high quality stuff, to go through there and choose the best ones and then develop them further. And then, yeah, that's basically, I think, the three definitions here. So you can see we fit into almost all three of them, right? We're generative design because we generate designs using our topology optimization algorithm. And our topology optimization algorithm sits on a CFD solver. I say, you know, I say we're a generative design tool and we're also topology optimization. So we have the paradigm of generative design, and that's the way to get the most value out of our tool. But really the concrete thing we're doing is topology optimization or fluid topology optimization.